What we're discussing today is the mathematics of the COVID-19 pandemic and its impact on South Africa. Now, exponential growth and the graphs that we see every single day sounds relatively simple, but it's quite difficult to understand. And the problem with EPD is that when we see exponentiality, it's typically too late. So we've seen these curves plotted worldwide. It was plotted in Wuhan with the first outbreak, plotted in the movement. And it plots to a graph that grows incredibly rapidly. So what does this mean? It means that there's a multiplication factor, which is a factor of the new cases today divided by the new cases of yesterday. And you can see the increase of that number and what it does to the numbers. So the equation is the number of cases change over a day equals the average number of people somebody infected on a day times the probability of being exposed. And then using simple factoring, you can simplify the equation. You factor out the n, and it comes to the following: 1 plus e times p times n. And that's the multiplication constant that you use in multiplying to get to exponentiality. It's far easier to see exponentiality in a logarithmic scale, where every 10 that you see is to the power of 10. So it's 100,000, 10,000, 100,000. So when you plot the pandemic, you will see the interaction with time. We took 20 days to reach 1,000, 13 days to reach 10,000. And that's called a linear regression. Linear regression is used specifically so that we can extrapolate the data. And as you can see, every 16 days, according to this data, you will find the times 10 to the power of 10. So within 30 days, you would find a factor on the 5th of April reaching 1 million, then 10 million, then 100 million, and then 1 billion. So this predicted that on the 9th of May, which is today, we would have had 100 million cases, but it didn't happen. The question is, why didn't this happen? Well, the simplicity is the curve is not following the rules exactly as we discussed. The biggest reason why it's doing that is there's a finite amount of people that can be affected by the virus, which means that if you've got one population pool, the chances of infecting somebody who's already infected is 0. So the two things that can affect the increase is E and P, which is the number of people infected and the probability of the exposure becoming an infection. The question is, how do we do that? So first, we look at the logarithmic scale, and we find that it becomes a logistic curve. Logistic curve looks exactly the same as the exponential curve in the beginning, but it flattens out as you reach the population size. So it's important to mention that true exponentiality doesn't exist in reality in the world today. It's a mathematical concept. The point where the change goes to 1 is called the inflection point. That means on that day, the amount of newly infected people are the same as the newly infected people yesterday. It does not mean it's declining. It means it stays the same. And then as it grows, this constant decreases, and we get to a flatlining. So the growth factor, as we said, is the new cases one day over the new cases the previous day. And that becomes 1 at the inflection point. So looking at the data that was started extrapolation on the 3rd of March, we see the multiplication or the adding of people, and we see the growth factor. So the growth factor was 1.37, 1.19, and this is what it means. It means that exponentiality is there because the number is larger than 1. At the inflection point, it stays at 1. Beyond the inflection point, it decreases. So when we look at the next set of data, it says 1.15. And if we now can look at reducing that to 1, it doesn't look like a big reduction. We look at the difference between 1.15 and 1. It doesn't look in numbers like a big reduction. But when you put this into the multiplication of exponentiality, it becomes a massive factor. So the inflection point is where it will max out at 2 times inflection, the pandemic. Larger than 1 means you in exponential growth, and larger than 1 means that the linear curve is still growing. It's not flattening off. Now, looking at South Africa, it's important to note that South Africa is at 1.57 yesterday, which means that we're still in exponential growth. What can we do to shrink this? Everything we've done to date. We're talking about wearing masks, social distancing, washing hands. We're talking about lockdown mechanisms. Why? Because we want to flatten the curve. So flattening the curve means that you take it to 1. And if you don't, you get the exponential factor. So looking at the numbers, the reduction of 1.15 to 1.05, if you've got 1.15 and you extrapolate that for 61 days, you get 105 million new cases. When you take 1.05 over 61 days, you get 411,000 cases. That's a monumental difference.